Good afternoon to all of you. Now we have to see the new source of noise in your communication system. Basically, in your digital communication system, that is called as intersymbol interference noise. Write down this one. Intersymbol interference noise. Here, up till now we have seen your main source of noise is the noise which is introduced by channel, that is called as channel noise. Here we have to consider this noise is nothing but additive with the nature of white. Its power spectral density, we will get a uniform power spectral density for all frequencies, that's why it is called as a white noise. Gaussian, it follows the central limit theorem, so it is called as Gaussian and noise. So channel noise we have to consider additive white Gaussian noise. In your digital communication system, transmitter generates the noise which is called as quantization noise. At receiver is not able to predict the transmitted signal or reconstruct the original signal. This noise is called as probability of error noise. So here we are having the quantization noise, channel noise W of t, quantization noise Q of t, and detection noise, that is a epsilon of t. Again we are having the new noise which is called as intersymbol interference noise. Which is also called as ISI noise, intersymbol interference noise. Write down intersymbol interference noise, that is capital ISI, occurs when a pulse, ISI noise occurs when a pulse spreads out in such a way that it interferes with adjacent pulses at the same instant. Example, assume polar non-return to zero noise. Assume polar non-return to zero line code. Here we have to send data 1 with this 0 minus TB polar NRZ non-return to zero line code. Here you have to send data 1 with the pulse from width TB by 2 and minus TB by 2. Similarly, for data 0, this one is TB minus TB. This one is channel input. Pulse width TB. On the communication channel, we have to send the data, here rectangular pulses, 1 0. This data 1 is sent with the duration of TB. Similarly, data 0 is sent with the duration of TB with reverse polarity. At channel output, now this signal is received by your receiver. Here this signal is spread out. Same signal with the duration of TB, it will get spread with the duration of 2 TB. So now here we are having the sequence of these pulses. Sequence of pulses, as the duration of this signal is get delayed, it will interfere with adjacent pulses. For example, for the input data sequence, here we have to consider the input data sequence with the value 1 0 1 1 0 1. For your example, we have to consider input data sequence 1 0 1 1 0 1. It is going to transfer via this channel. So input to this channel. Now we have to send this sequence with 1 0 1 1 0 and 1. This is the input sequence to your channel. At output, we will get these values. This is the sequence 1 0 1 1 0 1. Input to your channel, which each pulse, rectangular pulse of the width TB, So at output of your channel, every pulse is get spread out, or we can say that this pulse is get delayed, or this transmission from transmitter to channel, and the channel gives the delay. So due to this delay, the width of pulse is get spread out. This TB becomes 2 TB. So as this is 1 0, this one is 1 1 0 1. So when we concentrate on this 0, so this pulse which is corresponding to 0, it will get interfere with this one and this one. So there is an overlapping between these two pulses, adjacent pulses. So this noise is called as intersymbol interference noise. So our target is we have to minimize this intersymbol interference noise. So for this case, we have to see some mathematics regarding this one. Here we have to consider your pulse amplitude modulated system. For this one, pulse amplitude clock pulses are given. Here input binary data, that is dk. After this one, we will get a modulated signal with pulses A of key, transmit filter with impulse response G of t. Then we will get S of t, channel with impulse response H of t. Here this input is x0 of t, at output we will get x of t. Receiver filter with response c of t. At output we will get y of t, which is get sampled, and we will get y of ti. Here sample at time ti is equal to I into bit duration, capital TB, and finally it is given to decision device. Here input is threshold lambda. Here we have to make two decisions. Either this is 1 if this y of ti is greater than lambda, 0 if y of ti is less than lambda. Here input binary data with sequence b of k, rectangular pulses or any pulses, they are get pulse amplitude modulated. Here amplitude is going to change in PAM, so at output we will get a of k, almost impulse with a very small duration. So at here it is get multiplied with your transmit filter with an impulse response g of t. At output we will get s of t. Then it is an input to our channel with a impulse response h of t. Then it is given to the receiver. Before receiver we are having x0 of t. Here noise is going to add. Here we have to consider w of t. It is a white noise. This is a white noise or be specific. This one is adaptive white Gaussian noise. Now input to your receiver x of t, it is nothing but x0 of t plus w of t. At output we will get y of t, which is get sampled at a time ti is equal to I into capital TB. At output we have to make a decision. Here we are having the decision threshold lambda when one occurs if y of ti, this particular sample, is above the threshold value, that is lambda, then we have to justify this as a 1. 0 if y of ti is less than lambda. Is less than lambda. So here PAM, write down PAM modifies input binary sequence. PAM modifies input binary sequence BK into new sequence of short pulses, which are approximately equal to unit impulses. So depending on this one we are having the AK, which is approximately equal to +1 in polar form and -1 if this BK is equal to 1 and BK is equal to 0. Here BK is the input binary sequence which is given to pulse amplitude modulated system, which will convert into a unit impulses where AK is equal to +1 if BK is equal to 1 and AK is equal to -1, if BK is equal to 0, then S of t, for this case S of t here, it is get this sequence AK is get convolved with G of t, so we will get S of t that is equal to summation over k, AK is get multiplied or convolved with filter coefficient. Every filter coefficient is get convolved with AK. So in this way we will get S of t that is equal to summation over AK get multiplied with G of t minus k TB. So here we will get output Y of t. This S of t is given to the input to your channel with a impulse response H of t. The channel gives the output x0 of t. It is going to add with your noise W of t, which is the adaptive white Gaussian noise. So X of t is the input to your receiver, and finally we will get Y of t as a output. So Y of t is given as mu summation over k, that is AK into P of t minus k TB plus N of t. So output here Y of t is equal to mu is a scaling factor, summation over k, AK, this is a pulse amplitude modulated signal, AK sample value is multiplied with your P of t minus k TB. This is a pulse which is given as t minus k TB plus N of t. N of t is your nothing but noise. So here mu of PT, from this one we can say that at receiver we are having the Y of t that is equal to mu scaling factor summation over k, AK amplitude modulated signal pulse is multiplied with your P of t minus k TB plus N of t. Here for ideal case we will get mu of PT that is equal to G of t convolved with H of t convolved with C of t. Finally we are interested with your pulse P of t. From this equation Y of t, this is the output, I of output in terms of scaling factor mu summation over AK, that is modulated signal, pulse P of t minus k TB, which is get shifted, it is corresponding to your each pulse, plus N of t. N of t is nothing but your noise which is generated by your white Gaussian noise, out of which we are only interested with this mu of PT. This is a required signal PT at a particular time instant. T is equal to 0, we will get some pulse. Depending on this pulse, what is its width, height, amplitude, whether this is a greater than your threshold value, then we can say that this pulse is corresponding to your 1. When this value is below the threshold value, then we can say that this pulse is corresponding to your 0. Now we have to see its interference for your adjacent, that is Ti minus 1, I plus 1. Whether they are interfere with this one, depending on this one, this is called as ISI noise. Out of which we are interested with this P of t, which is get multiplied with your scaling factor mu, that is equal to G of t. How we are going to represent this P of t? It is nothing but a result of double convolution. Convolution between these three filters, response of this filter, G of t, this is a impulse response of your transmit filter, is convolved with H of t. This is corresponding to your channel, impulse response of your channel, and this C of t is a impulse response of a receiver. So how we are generating this required pulse in time domain P of t which is get multiplied with your scaling factor mu, that is nothing but it is a result of double convolution. G of t is multiplied with your h of t convolve with c of t. So here by assume that we have to do normalization or this p of t. So after normalization p of 0 is equal to 1. Normalize this pulse p of t, that is p of 0 is equal to 1. So here in frequency domain we can see that mu of p of f, that is equal to g of f, frequency response of your transfer filter, multiply with frequency response of your channel multiplied with frequency response of your receiver filter. So y of t, in this way we will get a y of t. Now y of t is sampled at time, output of this receiver filter y of t is going to sample at time, that is ti is equal to I into Tb. Ti is equal to I into Tb. So here we will get for every sample value y of Ti is equal to mu summation or k is equal to minus infinity to infinity ak into p of in bracket I minus k Tb plus n of Ti, that is equal to mu into ai plus mu summation or k is equal to minus infinity to plus infinity, k is not equal to I, so here we will get y of Ti. We are having the sequence of pulses, that is 1 0 1 1 0. Here t0 is equal to 0, t0 is equal to Tb, Ti is equal to 0, Ti is equal to Tb, 2 Tb, 3 Tb, 4 Tb and 5 Tb. So it represents the pulse information. At Ti, I is equal to 0, we will get a first pulse which is corresponding to 1, second one is 1 0, third one 1. From this sequence we can say that 1 0 1 1 0 1. Here I is equal to 0, we will get first pulse, I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4 and I is equal to 5 with the duration of Tb. Now this pulse is going to send on a communication channel. From transmitter it will use the response, impulse response G of t, it get convolved with impulse response H of t, it get convolved with impulse response C of t. Now this same pulse is going to transfer, first thing transfer filter, here we will get new pulse. Now it will get transfer over the communication channel with a impulse response H of t, and finally it will get transfer over the receiver filter response C of t. Now along this journey, here response, its duration is Tb. Now this duration becomes larger. So here we will get duration of 2 Tb. So whatever the output y of t, it will includes the two types of noises. First one is interference noise and second one is your wide Gaussian noise n of t. So this output y of t is get sampled at Ti is equal to ITB. So every impulse is get sampled. So we will get y of Ti, that is equal to u of AI, it is corresponding to your signal. Here mu summation over k is equal to minus infinity to infinity. K is not equal to I. K is not equal to I. This will indicate that this is your pulse. When we are interested with this third pulse, we have to find out the interference regarding this remaining one. Suppose this is your I. So here we have to consider that the total value for other pulses other than I. So response of I is given as scaling factor multiplied with your AI. This one is AK P of I minus K into TB plus N of Ti. This N of Ti is nothing but the noise generated by your channel. That is a white Gaussian noise. So here this first term is nothing but, write down here, contribution of ith transmitted bit, write down contribution of ith transmitted bit. This term is nothing but contribution of ith transmitted bit. Then remaining term, this one, write down here, intersymbol interference, intersymbol interference ISI due to the pulses before and after the sampling instant Ti. ISI due to the pulses before and after sampling instant Ti. Actually this is your intersymbol interference noise. From this one only we are interested with this one. Scaling factor multiplied with your AI plus N of Ti is given as a noise sample, write down here, noise sample at Ti. Noise sample at Ti. So how to reduce this noise? A single pulse, see here, we have to transfer this pulse, one, whatever its size, P of T, whatever its size, either it is a rectangular or sinc function. Now this pulse is going to transfer over transmitter to channel to receiver. Along this journey, this will get delayed and output we are having the intersymbol interference noise plus the noise generated by your channel, that is a adaptive white Gaussian noise. We can overcome this noise as we can overcome this noise by increasing output signal to noise ratio. By increasing output signal to noise ratio. So for this purpose we are using match filter. So match filter gives the performance, it will increase the output signal to noise ratio. We have to design such a filter, its filter coefficient h of t, that is equal to k into g of capital T minus small t. We will get a various coefficient of a filter which will minimize the error or which will improve the output signal to noise ratio. So here when we use the match filter, we will get this n of t is approximately 0 or this noise is negligible. So remaining noise, this is the desired part from this output, this one is ISI. So how to remove this noise? So write down, to determine the pulse waveform P of T for which intersymbol interference, that is ISI, is completely eliminated. is completely eliminated. Here, to eliminate this intersymbol interference noise, we have to work out on the pulse which are going to send over this transmission channel. That is P of t. What should be the shape of this pulse? Then what is its width? That is how much duration it is going to valid. So depending on this one, we have to use rectangular pulse or sync pulse. We are having the two solutions. First one is Nyquist criteria. Write down this. First solution is Nyquist criteria, and second one is raised cosine spectrum. Second one is raised cosine spectrum. We have to minimize the error which is occurred in your communication channel. This error might be due to your quantization noise, detection noise, white Gaussian noise, or intersymbol interference noise. So we require some estimation. So give a heading: mean square LMS, least mean square error, or minimum mean square error. Here we are having the signal Sn of f, that is a signal is going to add with your noise W of n, noise x of n, optimum linear filter. At output we will get y of n, and here we will get E of n. In this one, minimum mean square error for this system, for this receiver, input is S of n signal which is get modulated and get traveled over your communication channel. Due to this one, noise is added, that is W of n noise. Here we have to consider this is a white Gaussian noise with a zero mean, which is a input to your filter x of n, that is equal to S of n plus W of n. This one is the input to your linear filter. At output we will get y of n. Now here desired output d of n, this is a desired signal d of n. Here we can see that desired signal, it might be S of n, or the signal which is going to transmitted from your transmitter, this is your d of n. So we are going to compare this signal d of n minus y of n, it will give E of n. So here we can see that E of n, this is a error signal, E of n, that is equal to d of n desired signal minus y of n. So our target is we have to design such a filter, this optimum filter, in a such a way that we will get this E of n with minimum value. To calculate it's a mean square error. To calculate mean square error, we have to take expected value of E square of n, that is equal to expected value or this d of n minus y of n. So here expected value of E square of n is nothing but epsilon. So this epsilon stands for mean square error, and we have to design such a filter, optimum filter, which will minimize this mean square error, which will minimize this mean square error. So here we have to design such a filter square. So design of such filter, write down winner filter. Winner filter. We have to consider the filter of the length capital M. Write down filter length capital M with the coefficient filter length capital M with the coefficient hk, where this k is ranging from 0 to m minus 1. 0 to m minus 1. So for this filter, its length is capital M. We will get a coefficient hk, where k is ranging from 0 to minus m minus 1. So whatever the output y of n, here this y of n, it can be given as convolution of this filter coefficient and this x of n. So here y of n is nothing but coefficient h of k into x of n minus k over k is equal to 0 to m minus 1. So here this epsilon is given as expected value of dn minus this is nothing but summation over k is equal to 0 to m minus 1 h of k x of n minus k square. So here expected value of dn square is nothing but variance of desired signal. Expected value of dn square is nothing but variance of desired signal. Now here expected value of h of k for this signal, expected value of y square, expected value of h of into expected value of x n minus k square. This is the input sequence to this optimum filter. So can I say that x square expected value of this one? What is this one? Expected value of x square. Is it a autocorrelation? Yes or no? So here this y, it can be represented as summation over k is equal to 0 to m minus 1 h of k into autocorrelation of this L minus k, that is equal to cross correlation between this d and x. So output y of n, that is equal to summation over h of k filter coefficient get multiplied with your autocorrelation values of input signal x of n, that is equal to cross correlation between this d of n and x of n. So we are finding the relation. So here this equation is equal to cross correlation between d of n and x of n. Here This error function is nothing but the difference between desired signal and output of your filter, y of n. We have to find out the similarity or difference between d of n and y of n. Y of n is nothing but x of n multiplied with h of k. These are the filter coefficient. So ultimately we are finding the difference or relation between the desired signal d of n and x of n. So this y of n output, it can be represented as summation over filter coefficient multiplied with autocorrelation function of x of n, that is equal to your cross correlation between desired signal and input x of n. So in next lecture we are going to derive this filter coefficient for this winner filter, and what are the error? Here we will get some error. We have to minimize this error E of n. Again we have to give a feedback. As per this error, this filter coefficient are going to change. To minimize this error, we have to change the filter coefficient. At receiver side, we have to design such a filter. That means we have to design such a filter coefficient which will give the minimum error. Thank you.